This is our project exploring how to improve models for handwriting recognition. Handwritten text recognition is a critical task with applications in form digitization, identity management, and archival retrieval. Among the many types of handwritten content, names hold particular importance as they frequently appear in structured documents and are essential for tasks such as indexing, searching, and verification. However, there are many challenges in accurately recognizing handwritten text, including the variations in individual handwriting styles, overlapping characters, and the presence of noise in scanned or photographed images. The focus of this project was to develop a system for handwritten name recognition. We utilized a convolutional recurrent neural network as the baseline model due to its ability to extract spatial features using convolutional layers and model sequential dependencies with recurrent layers. While the baseline CRNN achieved reasonable performance, it encountered difficulties with ambiguous and noisy inputs. To address these limitations, we explored the integration of attention mechanisms into the CRNN architecture. Attention mechanisms are designed to dynamically prioritize specific parts of the input sequence, potentially improving recognition accuracy, particularly in challenging cases. Although implementing this approach introduced significant technical challenges and was ultimately not fully integrated, it provided valuable insights into potential enhancements for handwriting recognition systems. The ability to accurately recognize handwritten text has broad applications in both industry and research. Current systems perform well on printed text, but often fail to generalize to handwritten content, which exhibits a high degree of variability in style, structure, and quality. Handwritten name recognition is particularly relevant due to the frequency with which names are used in forms, documents, and databases. This project aims to address these challenges by leveraging deep learning techniques to improve recognition performance. CRNNs are a well-established approach in handwriting recognition, offering strong baseline performance by combining spatial feature extraction and sequential modeling. However, traditional CRNNs process all input sequences uniformly, which can result in suboptimal handling of complex or noisy inputs. Attention mechanisms have been shown to improve performance on sequence-based tasks by focusing on the most relevant parts of the input. For handwritten names, such mechanisms could enhance the model's ability to discern individual characters in overlapping or degraded text. This motivated our exploration of an attention-augmented CRNN architecture with the goal of improving robustness and accuracy in challenging scenarios.
This project utilizes a diverse dataset of over 400,000 handwritten names, which were originally collected through charity initiatives. The dataset is split into two categories, first names and surnames. The data is organized into training, testing, and validation subsets, with 331,059 images allocated for training and 41,382 images for each for testing and validation. Each image is paired with a corresponding label designed to facilitate straightforward extension or adaptation to other tasks. The size and structure of this dataset provide a comprehensive foundation for developing, testing, and evaluating handwritten recognition models.
So going a little bit into how we went about pre-processing the data. So the first thing obviously is we wanted to do some feature engineering. So, as we analyzed the data, we noticed that there was some discrepancies between like the top 10 names, and we saw that there were a lot of empty fields. And so with that, we wanted to make sure we removed null entries and also any unreadable or empty samples. And then we also wanted to make sure that we were standardizing all of this, so we put them all uppercase. And then as far as the imaging pre-processing went, we made sure that they were all in a grayscale conversion and then resized them to 256 by 64 pixels, just so that way we made sure that everything was on the same just normalization. And then we did it within the range of 0 to 1. And as far as data augmentation went, so for faint or overlapping characters, we just added padding during that image pre-processing.
We began by implementing a baseline CRNN model, which included a series of convolutional layers for extracting spatial features, followed by bidirectional LSTMs for modeling sequential dependencies. In our initial plan, we chose cross-entropy for our loss function. We chose CTC loss over entropy loss because it is specifically designed for sequence prediction tasks with variable length input-output pairs, like handwriting recognition. Unlike entropy loss, which requires explicit segmentation of input data, CTC loss automatically aligns input features with output labels, eliminating the need for pre-segmented data. This flexibility allows the model to focus directly on learning character sequences without additional preprocessing. The output of the recurrent layers was passed to a dense layer and trained with the CTC loss function, which computes the alignment between the predicted and ground truth sequences. The baseline model achieved subpar accuracy, but struggled with challenging samples such as overlapping or faint characters. To address these challenges, we introduced an attention mechanism after the LSTM layers. The attention mechanism computes a weighted sum of the LSTM outputs where the weights are dynamically learned during training. These weights allow the model to focus more on relevant parts of the input sequence when predicting each other. We modified the CRNN architecture by integrating this attention mechanism, replacing the direct output of the LSTM layers with the attention-weighted context vector. This required updating the decoder to account for the attention-modified outputs and ensuring compatibility with the CTC loss function.
So now let's go a little bit more in depth into the connectionist temporal classification function, aka the CTC function. So as said on the previous slide, this function was designed for sequence-to-sequence problems with unknown or variable alignment. And that's why it is best suitable for handwriting recognition with our varying character counts. But let's go a little bit more in depth into how it actually works. So the CTC function helps predict a sequence of characters, including repetitions and blanks. How does it do this? Well, it processes input sequence by breaking them into smaller time steps. For each time step, the model predicts the probability distribution over possible characters, including a special blank token. The blank token accounts for gaps between characters or repeated elements. And here's where the CTC shines. Instead of requiring precise elements between predicted characters and the ground truth, CTC finds the most probable alignment by examining all possible paths through its sequence of predictions. For example, let's say the ground truth is the word cat, and the model predicts CAAT. CTC can collapse repeated characters and blanks into the correct sequence. This flexibility allows the model to handle overlapping or faint or irregular handwriting without being constrained to rigid alignments. So why is this important for our case? Well, traditional loss functions often struggle with input and output mismatches, but CTC accounts for variability. By minimizing the probability of incorrect alignments and maximizing the probability of the correct sequence, the model learns to predict characters accurately under a variety of conditions. In essence, CTC enables our CRNN model to decode handwritten text effectively, even when dealing with noisy or overlapping inputs. It bridges the gap between what the model predicts and what the ground truth sequence should be, making it a cornerstone of our training process. So now let's move on to training the model. So here are all the parameters that we have in our model. First, let's start off with a look at the training and validation data. We see that we trained the model on a fairly large subset of 50,000 images and validated it on 5,000 images. Our training configuration is we use the Atom optimizer with a learning rate of 0.001 for gradual improvements. We use a batch size of 96 and also 20 epochs. Our loss function, as we described on the last two slides, was the CTC, aka the connectionist temporal classification loss function.
So after the training of the model, we got a character accuracy of around 85%, and a word accuracy of 69%. And one of the struggles that we really faced while we were doing all of these model evaluations was even just running our model took it took an extremely long time just for each of the epochs just to run. And so fortunately, we were able to get it to run through and get these. And then Phoebe will bring it home by talking a little bit about just like our conclusion and some limitations and improvements that we have for the future.
So our intended project focus was to investigate integrating attention mechanisms into a CRNN model for handwritten name recognition. So while we couldn't implement the attention mechanism successfully, we successfully built a CRNN model that achieved strong results with 85% character accuracy and 69.2% word accuracy. So the gap between these accuracies shows that the model struggles with predicting entire sequences, especially when characters overlap or are noisy. Adding attention mechanisms into our model could help by allowing the model to focus on the most important parts of the input image, which could potentially improve word level accuracy and make predictions more reliable overall. For future improvements, we could implement training of our model on the full data set. So as we mentioned before, the full data set had over 300,000 images, and it took several hours to download. So this made it impractical to train on the entire data set, which is why we only used 50,000 images in our training set. And also, we also face challenges with tuning the hyperparameters of the model. Finding the best combination of hyperparameters required a lot of trial and error, and using grid search and random search to guide the process took a really long time. So while building the CRNN model, we ran into technical difficulties like mismatched input sizes while debugging, and also while we were trying to implement the transformer into our model, we ran into difficulties with modifying the CTC loss function to support an attention mechanism. So for future improvements, we could train the model on the full data set, as I previously said, to better capture the variability in handwriting styles. Increasing the training epochs beyond the 20 we use could also improve accuracy further. Exploring attention mechanisms remains a high priority as they could help the model focus dynamically on key parts of the input and improve both character and word predictions. Other advanced methods like transformer-based architecture or beam search decoding could also make predictions more accurate and robust. For our resources, we used this main Kaggle dataset.